Okay, very good. So what we said is that we want to do topology in non-linear spaces using basic language of metric spaces. All right. So there are several words over there, and we will carefully make the definitions. So mainly Rn and occasionally Cn. So let's not even say using. Okay, so I will not again define a non-linear space, but remember what it is. It's just a finite dimensional vector space, real or complex, mostly finite dimensional for us. It does not need to be finite dimensional. With what idea? That there is a notion of measuring the size of a vector. Only the zero vector has zero size. Size is always greater than or equal to 0. Then you have this homogeneity condition. That is, if I scale a vector, then its size gets scaled by the size of the scalar, where the scalar has real or complex has its usual notion of size. And then the all important triangle inequality. Okay. We saw examples of non-linear spaces where usually we will just use the Euclidean norm, that is the usual distance function from the origin. So the size of a vector is you just square the sizes of the norms of the coordinates and then take the square root. But instead of square, we can use other exponents, and we have seen the case of using 1. We have also seen the case of using infinity, which is interpreted as taking the supremum of all the sizes of all coordinates. We have made some noises about saying that, which choice I make does not really matter, but we have not made that precise. So that is something that is left to be done, as is the case of using exponents p other than these. So we also said that an exponent, any p that is greater than or equal to, can be used. So that is something that is left. But I do not want to take up the thread there. Instead, we will start with metric spaces once again. Okay, so what is the definition of a metric space?
So it's a collection of points along with a way to define a distance function on them, such that the distance function satisfies 3 particular things. One is that it is positive definite. So it is.
So let me just start writing this down. So definition, metric space again. So what did we call a metric space last time? X or M? I think X. A set S, X. A set X with a function, distance function from X cross X to. By the way, just a funny little fact, that non-negativity of the distance function is something that can be deduced from the 3 axioms that we write down. But we don't care about such things too much. Math is more than axiomatic fun and games. So, all right, the function such that. Okay, so first is d of x comma y equal to 0 if and only if x is equal to y. Then we have the symmetry property. And then we have the triangle inequality. So d of xz is less than or equal to dxy plus dyz. And main examples for us are going to be any non-linear space with what distance function? Yeah, what distance function?
dxy was norm x minus y.
Correct. You just take the difference between the two vectors. And the properties, as we saw, are really obvious. The third one requires a slight amount of work. And then we also saw that any subspace, we will use the word subspace. Subspace will mean a subset of whatever set I'm considering along with an inherited structure. Okay. But here, any subset of a metric space with the same distance function. I mean, same, pedantically, the restriction of that function from x cross x to your subset cross itself. All right. So we want to do topology with this. And that means that we define open and closed sets. And after doing that, I will define a topological space. So far, I have not said what topology means, but we will come to that. By the way, so I said norm-linear space. That can be any norm really on the space. And we will see that for our spaces Rn, the norm does not really matter because it will give the same definition of the induced topology. So let's come to the topology. All right, so let's again recall the definitions. So what was for x in a metric space X and some real number R, let's say greater than 0. We had the open ball around X with radius. So what was it? BRX. What was that by definition? It was simply the set of all points around X. So Y in X such that the distance between X and Y is strictly less than R. And the closed ball, for which I use that notation. We will generalize that notation soon, and then we will justify why it makes sense for the ball. It seems to be the exact same thing with this weak inequality. That makes a lot of difference topologically. Okay, so very well. Now let's define what an open set is. So just a series of definitions. Oh, okay. I said union of balls, but of course I mean open balls. So just to emphasize, arbitrary union of open balls. In other words, I can take finite union, infinite union, any kind of union. And the way I have set this up, then perhaps we mean a closed set is arbitrary union of closed balls, but no, it doesn't really work that way. So a closed set
Complement can be covered with open balls.
No, sorry, say that again, please. This is your definition of what?
Whose closed set. Whose complement can be taken as a union of arbitrary open balls.
But an arbitrary union of open balls is what I've
open set, complement of open set.
So a closed set is not A. Just say X minus an open set. Okay. All right. So I'm fully aware that I'm just throwing definition after definition at you, but at some point it's going to stop. We do not have very many more definitions. And these definitions are extremely important definitions. Every time you make a definition, you really have to justify, is it really worthwhile to make this new word? But we will see that these words are really very worthwhile. And we want to talk fluently in the language of these words and a few more. Okay. So nonetheless, when we make a definition, we really need to see examples.
So one thing, this an open set, so that means it's fixed. So does it depend on X?
Yes, absolutely. So absolutely. So let's see. So right here, let me make it an open set of X. So absolutely, it depends on the metric space X. In particular, okay, so let me come to that. Let's see examples. Examples of open sets, and you can say open sets in Rn, correct? But before that, some simple examples. Thumb examples. The empty set is open because remember a set is called open. So I fixed a matrix space X, so I know the metric, and an open set is an arbitrary union of open balls. So how is the empty set an open set? I mean, it's a dumb, but we will say it once. So what union gives me the empty set? Yeah, so remember, union means I have given a family of sets, that is a set of sets, and I take the union of all the sets in this family. So here I'm taking the empty family, correct? Okay. So very good, open sets. Then, of course, X itself is an open set. What do I do? Come on, I mean, there is nothing to this. Okay, so maybe
we can pick a center and take arbitrarily large open balls.
Right. The point is the union should be taken over every single point in the metric space. Right? So this is the union of what radius do I take? It doesn't really matter. But any R will, but of course, any R greater than 0 will do. Okay, so notice one thing in the definition of a ball, I always took R to be greater than 0. In particular, if I actually take a ball, the ball will always be non-empty. The center will always be there. Okay. Okay, so those are open sets. And then there are other examples. So for example, a ball itself, right? So any ball. And so at this point, I would like you to think back about the pictures that we drew in the first lecture. Right? Depending on the norm that we took, we had the inside of a circle or the inside of a square, which was with sides parallel to the axis, but also a diamond-shaped square. Right? So depending on depending on which which norm I used, I got different shaped balls. But I want you to look back and recall our discussion that a ball of one kind always contained balls of the other kind inside that. So with this in mind, what you should realize is that if I define the collection of open sets inside R2 or Rn in general, using any one of these three norms, then I will get three different schemes of open sets, right? A priori. Because remember, what an open set is really depends not just on X, but on the metric that I have put on that. However, because of this nesting property, you should convince yourself that the collection of open sets that I get in each one of the three different schemes really stays the same. We will write this down when we define what equivalence of norms is. But anyway, so those are some open sets, and we will see lots and lots of them. But some examples of closed sets now. Because the empty set is open, the entire space is a closed set. Because the entire space is open, the empty set is closed. But more interestingly now, you can say that any here. So visualize this as follows. So let's just take the usual circle. So I'm taking the usual Euclidean norm. Let's say in R2, if you will, so that we can visualize. And now I'm taking the disk, the closed disk, that is all the points that are at distance less than or equal to 1 from the origin. So can you visualize and see that this is a closed set? Let's look at the definition. What is a closed set? It is the complement of an open set. So what we really are saying is that if I take all the points that are at distance strictly greater than 1 from the origin, then they form an open set. I'm just translating, nothing else, correct? So because all the y such that okay. In fact, let me not write this, because we are going to do this something like this more generally. But okay, can you see this? So I'm looking at all the points that are distance strictly greater than 1 from the origin. Why is this an open set? Can somebody tell me? Even a vague description is okay.
Sir, because if you take any point, let's say near the boundary of the ball, right? Like you can think about it as the whole space of the ball taken out of it. So if you consider any point, you can, no matter how close you get, let's say to that region, right? You can always construct some ball with a non-zero, like with a positive radius that doesn't cross that line. I mean, maybe this is too.
Okay, so let's draw this, correct? So what he's saying is that all this part, including the boundary, is taken out. And what we are looking at is the part that is outside this. And we want to say that is open. Again, remember what open is. Open means union of open balls. So this means that if I take any point outside it, I should be able to form an open ball around it, which stays outside it. And sure enough, I can do this, right? I can just take a small one. So this is one point. And again, to notice that no matter how close I come to the circle itself, I can still put a small ball around it, which still stays completely outside. Notice that if I took the complement of just the open ball, then this condition would have been violated. Because if I took any point which is at the distance exactly 1, And if I put a small circle around it, then it would have points both inside and outside, correct? Anyway, so you can try to take this as a small exercise that that does not matter. The closed ball is really always closed. Okay, so yet another example. Let us say the union of, let's say, x-axis union y-axis in R2. So that means this set. So that means this set. Only the lines. And of course, they're going off to infinity on both sides. I claim that this is a closed set.
So any path is closed, right? In the plane. Any curve.
Right. Okay. So let me.
In R2.
So we'll come to that in a moment. But first, is it clear that this is closed?
Similar design.
Right, because no matter where I take any point in any one of the quadrants, I can put a small circle around it, which does not intersect the axis. Right. Okay. Now, let us suppose I do the following. By the way, suppose I take not the entire x-axis and y-axis, but let us say I just take okay, so let's do the following. Suppose I delete one point from this set. Right. Does the set remain closed?
No.
Okay. Do you see what's happening? So let's write this down. So let us suppose that I'm saying x-axis. Let's just take x-axis minus the origin. Just the x-axis by itself is closed. Right? Is x-axis minus the origin, is that closed?
No, sir.
I want everybody to understand this, okay? Because slowly you want to, begin to gain some intuition where you can start visualizing open and closed sets and reason with them. So why is this not a closed set?
We can't draw a ball around a circle around zero origin.
Correct. So you see, this itself is I'm checking the so I'm going to draw it like this. Now to see that to check whether this set is closed, what do I have to do? I have to take its complement, and that means all the points that are either positive y coordinate or negative y coordinate or the origin, right? And I have to check whether this set is open. That means that I have to write it as a union of open balls. That means that given any point in this set, I have to put a small ball around that point, which lies in the given set. Now, this all works perfectly well for points that are above or below the x-axis, just as before. But it has to work for every single point. So if this set were closed, then I would have to be able to take the origin, which is not in this set, and put a small ball around it such that everything in that ball is in the complement of the set that I'm taking. But no matter how small a circle I take around that point, it is going to contain points of the x-axis. Okay, so I spent many words talking about this. You have to reach a point where you just see this and you say, oh, obviously this is not closed. Okay. So
Sir, I have a question.
Just give me a moment. So whatever mental distance you have to cover to reach that point, you have to give it that time. Okay. So now we will come to questions. So we will come to questions and comments. So there was a first comment which said that any path is closed.
It is neither. It is open, right? This set.
Okay, so that's a very good point, and let's backtrack to say this. This set is not closed, nor is it open, right? Nor is it open.
Yeah, so my example should be like continuous paths, R2, R2, they are always closed set.
Okay. So first we have to understand what a path means, but let's go one step at a time. So it is worth saying in the beginning, it is not necessary that a given subset of a metric space be either open or closed. There are lots and lots of other subsets that are neither open nor closed in general. Okay. But it really depends on how you define open sets. So in this in the metric space, we have defined open sets in a certain way. Okay, but this really depends on the metric. Okay, so the next comment was that any path is closed. So the question is, what is a path?
Any continuous function from closed interval a comma b to R2
So
or open interval a comma b. No, actually closed interval a comma b, but this path can also be no. Okay, it has to be a closed interval a comma b. Sorry.
Okay, so I'm just going to write this down because we should be careful. Okay, so comment. Any continuous path so any continuous, okay, I'm just going to write it verbatim and then we will work with it. Okay, any continuous path sorry, so how do you want to complete the sentence?
In R2 will form a closed set.
So the question is, what is a path?
Any function from in closed interval in R to a comma to R.
So let us say path equals a continuous function from 0, 1 to whatever space you are considering. Okay, from this to your space, so which is here R2, any continuous function to, let's say, R2. But one has to be careful here. Is a function a set? Remember, closed means it's, when I say closed, the word closed is applied to a set.
Image of the function. Image of the function that set 0, 1.
All right. So the picture in mind is that what you start doing is you just put your pencil at some point. So picture. You just put your picture. So you think of this closed interval 0 to 1 as a time interval, and the function as the trajectory of a point. So you start at some place and then you end up somewhere.
Excuse me, sir.
Yes.
Sir, can you please scroll up a bit because it's a bit difficult to see.
Okay. Okay. Is that okay?
Yes, sir, it's fine.
So the claim is that such a thing is closed. So visually this is appealing, right? But can we prove this? So you see how many things are involved over here. So you have a continuous function from the closed interval, and then there is R2. Then you are taking the image of this, and you want to say that such a thing is closed. This is a true statement, but in order to prove, just give me a minute.
Okay, sure.
So this is a true statement, and we will reach a stage at some point where you will be able to prove such a thing quite easily. So because we have not developed some terminology and some facts about that, the use of which makes this quite easy. But you can try to do this, you can try to take this as an exercise now. So this is a true fact. So this is true. True.
In fact, the more general version would be the compact function from any dimensional space. The domain should be compact and any dimensional space. The image. If that is
let's not do things that we have not defined, okay? Because it does not really serve the purpose of other people. We will come to it.
Excuse me, sir.
It's like the higher dimension analog of that real number functions that on closed interval, the range will also be closed interval.
Okay. So has this statement been proved? So this is analogous.
Yes, and this is one.
Okay. So all right. So all right. So this is analogous to. So let's write this down. Analogous to continuous image of a closed interval continuous under. Okay, so this sentence has gone out of control a little bit. Of a closed interval continuous. For f from 0, 1 to r, correct? I think this is what you're talking about. So I want to write the statement carefully so that everyone understands that this has been done. Okay, so please check whether what I'm saying is exactly what is. For continuous f, okay, what did you prove about the image of this? Because the word compact has not been defined, correct? So what do you know about the image of such a thing? What did you prove in analysis 1?
The image is a closed interval.
The image is a closed interval, right? Okay. So let us see. Oh, so is this closed interval just the interval from f of 0 to f of 1?
No, it can reach maximum and minimum.
Yeah, right. So you see, this is not something, it's not something that straightforward. Okay. And so instead of you're saying closed interval, you're saying closed set. Now this path, when you go to higher dimensions, it can go in multiple dimensions, and it can come back, intersect itself. It can do lots and lots of things. Nonetheless, some property that it does continue to satisfy is that it is going to be a closed set. Okay.
So one small question in this,
Yes.
x-axis minus origin is not closed. That thing I got. Now it's not even open because any ball we take near the or on the x-axis, then we'll have some points outside the x-axis.
Exactly. That's right. Exactly.
So from that, can we say that any continuous path is never an open set like that?
So any continuous path is never an open set.
I mean,
from where to where?
After a line, like a strip. So any ball we take, so some part will be outside.
Yeah, but you see, okay. You're talking about a function from the closed interval to R2, right?
Okay, yes.
Yes. But it might be, you see, the words open and closed are going to be applied to more general things, to any metric space.
Okay.
Right? Okay. So I'm not saying that what you're saying is wrong or anything like that, but the word metric space is going to generally apply to lots of things.
So even
in
path
particular,
has a more general definition.
No, the word path will still have the same definition. See, paths are very interesting objects and you will do lots and lots of things with them. But let's not go in this direction for now. Okay, so let's stop here and we'll move on. The definition of a path that is given here is correct, where you say the path is a continuous function from a closed interval, which you can take to be 0, 1, to really any space that you like. Such a thing is called a path in that space. And you can do lots and lots of interesting things with this. But our brief here is to do analysis, not so much topology, except what is really required. All right, but let's move on. Yeah, one point I do want to make here. So note that, I mean, really, this is part of the definition, but note that open and closed no, this sentence started badly. So, okay, let me ask a question. Okay, so we said that any subset of a metric space is itself a metric space, right?
Yes, sir.
So now look at the space which is the union of the two axes. That itself is a metric space. Yeah. Correct? Yes. So my question to you now is that suppose I take that space itself. Is it an open set? So if X is the union of the two axes, is X an open set?
No, sir, because there'll always be a point in like y-axis, like if you take a ball around X.
I think it should, because what do we mean by going outside? Yeah.
Right. Okay, so both answers are correct, but the point is you're talking about different spaces. So let's go back and see here. If I have X to be a metric space, then X itself is always open in X, right? So maybe we should emphasize that X is open in X. So if my topological space itself is that union of two axes, then it is open. And you see the balls in this space are now sort of interesting, correct? Because I'm still using the ambient Euclidean distance. So so you see the balls in this space are going to be interesting. If let's say I take a ball of radius 1 at a point on the x-axis, which is distance more than 1 from the origin. Then the ball is just going to be an open interval. But let's say I take a ball of radius 1 at the origin, open ball at radius 1. Then what am I going to get? I'm going to get a cross, except its 4 endpoints. That's going to be the open set in X, which is the ball of radius 1 centered at the origin. Or if I let's say go off center, let's say I go at the point 0.5, 0 on the x-axis. And I take a ball of radius 1. Then I will get sort of a cross, but a lopsided cross, where the horizontal length is going to be 2, because I have taken something of radius 1, but the vertical length will be less. Do you see what I'm saying? So maybe I should, okay, so let me see. So note that, really not my day, is it? Okay. Okay, so if S is a subset of a, then S itself has a collection of open and not simultaneously open sets. Okay, so so when we are talking about multiple topological spaces at once, then it is important to say open in what? So, and this is when we are talking multiple, I use, I'm sorry, I use the word topological space, which we have not defined, but we'll say multiple metric spaces at the same time. It is important to specify open or closed in, okay, again, this sentence has gotten out of control. It is important to specify open or closeness of a space of which, which topological, which space am I considering at the time? Okay, so it is important to specify okay. Let me try to rescue this. And we say that some set is open or closed. It is important to specify in which space. Okay, so I hope that this point is, clear. All right. Further definitions. For a point X in metric space X, a neighborhood. Okay, so let me not be lazy and write the full word at least once. Neighborhood of X is a set N such that X is contained in N, certainly. X is contained in an open set which is contained in N. So this may look like a strange thing, But I will first draw a picture. Sort of keep this in mind. So the picture to keep in mind is that here is X, and you have an open set, and then you have some neighborhood, whatever. So an open set, let's call it U. And this N. In other words, what we are saying is that this set N itself may not be open, but it contains an open set containing X. And if you just think about it for a moment, we, instead of taking open set U, we might as well take, oh, sorry, I have to make one more. Okay. If N itself is open, then we say that N is an open neighborhood of X. Okay, so is the definition clear?
Yes, sir.
Okay. So now I want to make a claim, which is claim. If a point X is in some open set V in some metric space, okay. So let me not even say that, because the word open for us always means that I have a metric space. So what happens then? There exists. Let me write this and I will then say such that okay. So what is being said is that if I have an open set and if I take any point inside that open set, then what do I know so far? All I know is that this open set is a union of some balls, correct? So every point in an open set must be in a ball that is totally contained inside that open set. So let's draw a little picture here. And sorry. So let's draw a little picture here. Okay, why am I not? So let's draw a little picture here. So this is some set, open set, correct? And now I have a point X in here. Okay, so now I'm not really sure why I'm not getting a new page. Maybe I have to start a new document. There is a bug here, clearly. Okay, so all right, so this is a set V, and I have some point over here. So all I know so far is that this entire V is a union of open sets. That means this point X, union of balls. So this point X that I have drawn inside must be part of some ball, right? So let's say I'm going to put a ball over here. So what is the claim saying that is new?
X is the center.
Right. So of course, X is not the center of the ball that I have chosen. There is no guarantee. But what the claim is saying is that I can always put a ball with the center at X in the given set. Okay, so I'm just going to draw this. So, which is to say that I can always draw a small ball around X, which is inside given V. And in fact, the way I have drawn it is that I have put this ball inside the ball itself, of which X was a part. But I can do that, right? So, okay, so let's try to make a proof out of this. And in order to do this, I should take the, so proof. And this is typical of many proofs that we are going to write. There is going to be some estimation, but you make the requisite terminology and the proof just writes itself. Okay. So by openness of V, what do I have? X is inside some ball which is contained in V, right? So this is a ball with some radius and some center. So let's give that a name. So let us say this is with some radius R with some center U. Okay, so this picture is a bit small. Okay, so all right, so I'm not sure why this is happening. All right, so I just migrated to a new note-taking program. So does anybody have any experience with this? Because okay, so no. All right, so I'll tell you what, we are going to just go to a new, we're just going to go to a new node today. Okay, and in fact, let's have, so this is nice. Let's, so I have this V. I have the point X in here, but X is contained in a ball. So this is V. This is B. This is some ball. So it has radius R around some point U. And now I claim that I should be able to put a ball inside inside the entire V, but in particular I will put it in the ball that I have drawn, such that I should be able to put a ball like that. Okay. So given X inside BRU side V, I want some radius delta. So let's write down that this radius is delta. And this radius over here is R, correct? I want delta greater than 0 such that X, of course, is in the ball of radius delta around X, but I want this inside the ball of radius U. And so therefore the whole thing will be inside V, which is what I claimed. Okay, so how to find delta? The setup takes more time than the proof.
Sir, R minus BU comma X.
Correct. So now notice what is going to happen. Basically, what I want happening is that when I take this distance delta around X, I don't want to go outside the ball. Which means if I take any point at distance, let's say at most delta, even if I take a point at distance delta, I do not want to go distance how much away from U? Distance R, correct? So, but that is very easy to arrange. So this suggests that I should give a name to a distance, right? Which one? Imagine that this X was going closer and closer to the boundary. Then delta would have to shrink, correct? In order to stay inside the larger ball. So the delta that I take should depend on which distance. In order to define delta, I should take in account the distance between
U and X.
U and X. Okay, so let D equals the distance between U and X. Then basically what I'm saying is that this distance D, and when I start going from X in any direction, I should not go distance more r or more from the center u. So choose, how should I choose delta? Such that if I first travel distance d and then I travel distance delta, I should still not be able to go beyond r. So let's just do it such that this is less than r. I think even equal to will work because we are taking open balls. Right? So maybe, so for example, G delta equals r minus d by 2 or something like that, whatever. Oh, by the way, so how do we know that, how do I know that r is greater than delta? Sorry, how do I know that r is greater than d? I'm doing r minus d, no?
Because x is in the ball.
Because x is in the ball. So x has distance less than. And now, it's obvious that if y is in this, I need to show we will be done by showing that this y actually lies inside the ball. Remember, so what I want is that anything in this ball is also in this ball. So what do I need to show? I need to show that the distance between u and y is strictly less than r. But distance between u and y is, come on, now just complete this. What is going to help us over here?
Triangle inequality.
Triangle inequality. So the distance between u and y is less than or equal to the distance between u and x plus the distance between x and y. And distance between u and x is what I call d. And this distance is less than, and this distance between x and y is strictly less than delta, right? So this is less than that. But I chose these things in such a way that d plus delta is less than r. So what this says is that any open ball, any open set, I can think of it as if I have a point inside an open set, then I can always put a small ball around that point in the open set. This is a small technical little thing, but it is quite useful. So this tells me that if I have an open set, then I can always form it in the following fashion. Take every point in that open set and put a small ball around it. And the entire open set is made up in this fashion. Okay, so this is useful in proving other things. So let me end by just stating some results, which you should do on your own. And this is where we will take it up next time. So theorem. Union of open sets. So this is all, let X be a metric space. Two. Intersection of two open sets is open. And therefore, by induction, intersection of a finite number of open sets is going to be open. Then there are analogs of this, just for emphasis, arbitrary So the reason why these are called 1' and 2' is because it's just taking the complement and doing basic set theory. Okay. And I think that with this, it's a good point to stop, because then we can define what a topological space is once we have these properties. So let's stop for today.